Hey everyone, welcome to this live stream. So I just want to say welcome to the new subscribers that I've had, and if you're new to this live stream series I'm doing, it will be every Wednesday night. I've missed a few recently, but hopefully going forward I'll be doing them every Wednesday. And I'll be talking about the way I use C++, which is a very limited subset of the C++ language, and not using many of the modern C++ features. So hopefully you find that useful. So if you like what I'm doing, subscribe to me on YouTube obviously, and on Twitter is the best way to follow me. And you can also follow my 10x editor development streams as well, which I typically do on a Saturday. So last stream, I'm trying to remember what I was doing. I was talking about my core library. So because I don't use STL, obviously I have to write my own container classes, and it's something I think every sort of low-level programmer should do because it's fun. It's good writing container classes, and it's not actually that hard, and you can get really significant performance gains if you know what you're doing. So hopefully this will be useful to you if you're thinking about doing that. So today I thought I'd do a deeper dive on my HashMap class. I've mentioned it a few times in passing, I think, but I haven't actually explained in detail how it works. So I've prepared a few slides just to explain the algorithm, and then I'll take you through the actual code. But as usual, ask questions as we go, and I'll try and keep an eye on the chat. So yeah, let's get started. So hash maps, obviously, it's for mapping one key to a value, and the key has a hash associated with it for fast lookups. I'm not going to explain hashes. I assume you all know what hashes are. And typically in a hash map class, you'll have an array of pointers to buckets. So many hash maps use buckets. That's because obviously multiple things can hash to the same value. My solution doesn't use buckets at all. It uses just a single contiguous sparse array. So it's just one allocation, one array, and the values are inserted in. Now, I should probably say before I start that I've been using this hash map that I'm talking about for over 20 years now, and it's pretty much the only one I ever use. So I'm happy with it. It's about as fast as you can get for most common cases. It has a few slight drawbacks over other things like the bucket system, which I'll come to probably at the end. But I find it to be, when I'm wanting to use a hash map, it's because I want something that's really fast. And this is about as fast as you can get, I think. So it's very, very simple. You won't find that much real complicated algorithms here. But as I said, I've been using it for a long time, and it's the one I always rely on. So yes, as I said, instead of using multiple buckets, it uses just a single sparse array. Now, one of the benefits of that is obviously that it's one less indirection. So when you're looking something up in this system, you have to find the bucket it's in, which is using the hash, and then go to the bucket and find the item you're interested in. So it's a sort of two-step process, whereas this is almost always a one-step process, and it's not jumping to a different memory and location. So it's going to be more cache-friendly. So in a very simple way, obviously, you just take the hash and mask off the lower bits, depending on the size of the table. So for example, say this is size 16, you're just masking off the lower few bits and using that as an index into it. And I will explain later, it's not quite as simple as that. I do actually do a little bit more before I use the hash. But for now, let's just assume I'm just masking off the lower bits of the hash that's being passed in as the key. And obviously, so that's index 1, it goes here, index 5, index 9, etc. Very, very simple. And in the best case, that's exactly how it works. You just have this sparse array. You just take the hash, mask off the index. that's your index, and that's where the value is if it's in the table. So you can't really get simpler than that. And in the best case, if you've got a good hash, I mean, obviously always a hash map relies on having a really good hash function. So we'll assume you've got one of those. And in the best case, this is what the hash map will look like. So the grey are things that have been added, and the white is just holes. So ideally you wouldn't have any clashes, and there'd be space between each one in case there are clashes, which I'll talk about in a minute. So it's just one big old array with a load of values scattered, well, evenly distributed throughout the entire array. So that's the best case. So typically you need this array needs to be like 4 times the number of things you're going to add into it so that it's sparse. Because if you filled it up entirely, then you wouldn't be able to deal with clashes. So it's important that it is sparse like this, and you do have holes. Like, a good example is like this. You have 1 and then 3 holes, and then 1 and then 2 holes, 1 and 2, 1 and 3, etc. It's important that it is sparse like that, which will make sense in a minute. So what do we do when we have a collision? Because obviously collisions are going to happen. Obviously you want to create the hash so that it has as few collisions as possible, but they're always going to happen, and you've got to obviously cope with it when they do. So here we've got the same 3 that I showed you just now, 1, 5 and 9. So I put a green line under when an item's been added in at the exact hash index that it wants to be. This will make more sense in a minute, but just keep that in mind. The green line means that is exactly where it is expected to be. So then we come along and we have another hash value, which just happens to end in 05 again, like the green one. So we want to put it here in number 5, but we can't because there's obviously already a value in there, a different key, but with the same hash. So we just add it to the next consecutive value. So very simple and very fast as well. So obviously when we're looking up a hash, we just do the same thing. We take the lower bits, masking off depending on the size of the table. We find it's at index 5. We go to 5 and we check, does this match the one I'm looking for? No, it's green, so it doesn't match the one I'm looking for. So we move on to the next one. Does that one match the one I'm looking for? Yes, it does. So that's the one I found. So we can do this as many times as we want. We can add, if we had lots more clashes, hopefully we wouldn't, but if we did, we can add them 7, 8, 10, etc. And when we look them up, we just iterate through each one until we find the one we're looking for, or until we find a space. So imagine if we were saying, does a value contain a hash that isn't in here, and the hash ends in 05, we would start here, check that one, and then when we get to an empty value, we stop because we know this table doesn't include it. So that's essentially the idea. We just start at the index that is expected to be at, and then just consecutively look into the next item to see if it's a matching one, and then when we get to the empty one, we just stop and give up. So that's why it has to be sparse. So ideally we would have lots of empty spaces, so we wouldn't have to iterate too many times. And that's why I said we need the ×4 capacity at least. So if you've got a good hash function which is evenly distributed across the whole hash, you'll have lots of holes, which is good. So we can afford a few collisions on each one. Hopefully it won't be any more than sort of 2 or 3 collisions on each one, and we just iterate 2 or 3 times until we find the one we're looking for. So that's a simple case of just one collision, and that's good. If we have many collisions, like I said, we just keep adding them to subsequent holes. So these are all empty. So if we've got these brown and purple ones all end in 05 in a hash, we just keep adding them here. We can't add them here because there's one there already, so we just add it here, and that's fine. It doesn't matter that these are hashes ending in 05, and that one's ending in 09, but that one's ending in 05. And that's fine, because like I said, when we're looking for it, we just start here and then just keep going until we find the one we want. Ideally, like I said, you wouldn't ever get something this bad, but obviously the algorithm's got to cope with it. Oh, hey GGN, so I didn't notice your question. What What's the biggest amount of hashes you have used with a scheme? I've used incredibly big schemes actually. The biggest one was for a big game engine where I was tracking every single allocation that was made in the game, which was like tens of thousands a frame. It was a very bad engine in allocation terms. And I was writing a memory system, and I needed to be able to have a hash map of the allocated pointer to where it came from, its tag or whatever. And it was an absolutely massive table. And like I said, I was using the pointer as a hash to look it up, and it worked very well. That was probably the biggest test of the system I've done, but I've used it, like I said, for 20 years in pretty much everything. So there's really no limit to the size. As long as you can allocate one big allocation that's big enough, then you're all good, really. But that is one drawback of this system. It does use up slightly more memory than some of the other like bucket-based systems. But if you're mainly interested in speed, which I usually am, then it's a good option. Okay, so moving on. So when we want to remove something, I mean, that's pretty much as complicated as it gets. So I've pretty much described the entire algorithm for adding and querying the hash map. That's very simple. The one slight complication with this system is removal of items. So let's take the real easy case. You know, we've got a green here, 05, we want to remove it, so that's fine, we just remove it. There's nothing clever we need to do for that. It's absolutely dead simple. The complication comes when you've got the case of lots of collisions and you want to remove one in the middle. So say we're removing number 6 here in the middle. So let's just quickly recap on what we've got. We've got hash ending in 3, so that goes into 3, that's fine. Then we add another one that ends in 3, so we have to add it to the next item, and the next, and the next. So we've got a whole series of hashes ending in 3 here. And then we've got blue, which is a different one, ends in 7, so it's put in at 7, and that's fine. That could have gone in there earlier before we added these, perhaps. And then we add another one ending in 03, so because we filled up all these and number 7 is filled up with a proper hash value, green underline, remember, then we have to stick it in number 8. So we've got a whole range here with 3s, 7s and 8s, and another 3, sorry. So we want to remove number 6. And obviously that's going to cause problems if we just simply remove it, because then we've got a hole. And say we were trying to look up number 8 and say, is number 8, what's the key, the value of the key number 8, or a hash ending in 3, sorry, it's this light green hash, whatever that is. That's what we're looking for. We would obviously start at 3 because it ends in 3, and then we would iterate until we get to a hole, and then we give up and say it's not in the table when evidently it is. So obviously we've got to fill this hole. We can't have a hole here. So obviously what we do is, in this case it's pretty simple, we just take this value and stick it into number 6. And we can do that because then it creates a contiguous array so that when we're looking for that we do find it. Bam, it's there. And this is probably the simplest case of removal. There are a few more slightly more complex. Let's look at another case. So again, we got the same thing here, these ending in 3, then we got the 7 ending in 7 there, and then this 3 again. And then we've got 2 more ending in 7. So we've added another 2 values, a hash ending in 7, and we've already filled up all these values. So it would go into here, but that's filled up. So we try the next one, that's full as well. So we stick it here, and the next one goes there. So again, we're removing number 6. And so we do the same thing as I just said. We remove from number 8 to number 6, and that's fine. But obviously, again, we've got the same problem. We've got a hole here again. So all we do is the same algorithm again. Obviously, we start from here and we find the last one that can go into this hole, which is the last 7. So it goes there and goes in. So then we've got a nice consecutive array of hashes ending in 3 and another consecutive array of hashes ending in 7. And we're all good. So obviously we've got to do the algorithm multiple times to make sure we get rid of all the holes. I mean, you could think, why don't we just say we're getting rid of number 6, why don't we just shift all of these left one? And that would be the sort of the way you might first think of doing it, but obviously that's wrong, because if we did that, then 7 would end up in 6. And this blue one ends in 7 has to go into this index 7. You can't put it in index 6 because it would never be found. When we look it up, we would say, okay, it ends in 7, I'll look it up, try here. But it would actually be one before. So obviously you have to be a little bit careful that you don't move an item to before where it actually should be, okay? So there are a few sort of subtleties in the algorithm. Okay, another question. How do you choose hash table size? Is it a prime number? No, so yeah, this is probably something I should have mentioned, but the hash table size is always a power of 2 in this algorithm. And that's so that we can just mask off the bottom bits. So if I go back to the beginning, so we're just using the bottom bits depending on the size of the table. So the bigger the table is, the more bits we can use of the lower size. I have got a version of the table which doesn't use power of 2 and it uses a percent modulo instead. But obviously a percent modulo is slower than just masking off the bits. So I prefer usually to use a power of 2 size table, but they're not primes. And the reason for that is because you're using a mask just to get the index. So, you know, it's a very, very simple. What's the index? Just mask off the lower n bits depending on the size of the table, and that's your index, and it's job done. So no divides or anything like that. So yeah, I was just saying you can't just shift all of them up to fill the hole, and you don't want to shift every single one, obviously. Ideally, you just want to shift the last one. It's like doing a remove swap last in an array to remove an item. If you don't care about the order, then you can just swap the last one in. Rather than shifting all of them up, you can just shift the last one in. You don't care that the order has changed, and it's much less moving to do than the other way. So let's look at one more case. I haven't done an animation for this, but it's fairly simple. So we've got these greens which are all hashing to the same index, or hashing to index 1. And obviously they just go in consecutive ones because of the collision. And then again we've got a hash ending in 4, so it goes into index 4. And another one ending in 4, so we put it in the next consecutive one. So say we want to remove number 5. How can I best explain this? I should have done an animation like the other ones. It was much easier then, but I ran out of time. What you've got to do is first of all scan back to the start of the array. So you scan back until you find an empty value. So you scan back to 1. And the reason for that is you can't just start here at index 5 or 4 and say, okay, is there another one of 4 and go on, because this one has an index of 1. So you have to first, I'll show you this when we show the code, it might be simpler to explain then. You first have to scan back to the start of the array, find this index, and then say, is there another one in the range between 1 and 4 that we can shift into this value, because there might be higher indexes which we can't shift back. Because like I was saying, remember I said you can't just shift, say, number 7 back because it's a higher index. So at some point we have to decide which are the ones that we can shift back. So we first have to find the start when we say, okay, is there anything between index 1 and index 4? And if there are, we can shift it back. So we have to check that we're not going to break the algorithm when we do our copying. But anyway, when I show you the code, hopefully that'll be a bit more simple. The other slight trickiness to this algorithm is you've got to obviously cope with wraparound. So say we insert a value at index 13, and then we have a load of other clashes that all want to be at 13, so we add them to consecutive, the next empty slot. When we get to the end, obviously we've got to wrap around and go back to the beginning. So that just adds a little bit of trickiness to the removal process again, where we've got to elegantly cope with wraparound. So again, if we were removing a value, we would start here, scan back to the start of the array until we find an empty one. That's the start. So we know anything between 13 and 1, we can shift backwards to fill any hole that we found. Okay, so question, what if instead of moving values around, you stuck an invalid value in a hole like -1? Yeah, you could do that. So we could just say, pretend it's filled and put some kind of marker value in so that when we iterate over them, we would just skip it and carry on iterating. And that would work. That would avoid the moving around. But the problem with that is your hash map would fill up. If you're doing lots of adding and removing, your hash map would just eventually fill up with empty values. And I guess you could do some kind of purge periodically to try and get rid of them. But it's not typically a problem because, I mean, this is a really bad case. Usually you don't have cases this bad in your hash map. So you'll end up only ever moving 1 or 2 values typically. It's very rare to have a cascade of removals, moving of items around. And the other thing to keep in mind is that this is an array of pointers. When I show you the class, I'll show you that this big old array is literally just an array of pointers. So all you're doing is swapping pointers around. You're not actually swapping the objects. I haven't actually shown this in these diagrams. So it's just an array of pointers and you're swapping the pointers, so there's no big deal to it. The actual items are stored in like an allocator array. I'll show you that in a minute. So yeah, the wraparound is the thing you've got to be careful of. I'm still paranoid that I've missed something here, but I'm fairly sure I've got it now. So yeah, other things to note about it. Like I already said, the size of the array is a power of 2. It doesn't have to be, but it just means you can use a mask instead of a modulo, which is a little bit faster. And arrays often grow in size of powers 2 anyway, so that's not really a problem. So resizing can be slow. So obviously, like I said at the beginning, the capacity has to be 4 times so that it is sparse, so that you can cope with clashes. So however many your maximum value is, it needs to be a quarter of the actual size of this array. So that means that when we resize, we've got to essentially add all values into the new size array. So we resize by doubling the size, creating a new array, and then we have to add in all the values again. So that's obviously can be quite slow. But there should be fewer clashes if there are any, because it's a bigger array size now. But typically when I'm using a hash map, I'll reserve it up front. Usually I know roughly the size it's going to be, so I'll reserve it to a nice big value. I mean, when I'm using a hash map, I don't usually care about memory so much. Well, when I'm using this kind of hash map, I don't care about memory. So I'll just reserve it to something quite big. So it doesn't have to resize that often. But it's not going to resize that often because it's growing in a power of 2. So yeah, it's going to be about as best as it can be in that case. But yeah, resizing shouldn't happen too much, ideally. So it's something to keep in mind. So removal can be slow. Like I said, the removal is the only complex part of this HashMap class, really. And so if you are getting lots of clashes and you're removing stuff, then it can be quite slow. But typically I very rarely remove stuff from HashMaps. I just find, especially in my current project, the 10x project, I'm using HashMaps in the parser all over the place, and I'm hardly ever removing values. I mean, there are lots and lots of huge HashMaps that I only ever add to. So yeah, it's not typically a problem for me, but if you're doing lots and lots of removing and you're getting quite a few clashes, you might want to look at using a different class than this. So those are just two things to keep in mind. You don't want to be resizing too much, and you don't want to be removing too much if you're getting lots of clashes. If you're not getting clashes, like I said, removing's a piece of cake. It's very, very simple and very fast. But if you are getting clashes, then it's bad. So I'll talk about the Knuth, I don't know how you say that, KnuthHash, probably when I show you the code, because that's quite important to get really good distribution. And as I said, this algorithm punishes you if you have a bad hash, okay, especially if you're removing. If you're getting loads of collisions and you've got a really bad hash, you're just going to end up with huge long arrays of consecutive things all hashing to the same value, and when you query it, it's going to start at the first and then just iterate through all the subsequent ones, and it's going to be very slow. So it rewards you for a really good hash when it's really evenly distributed across the whole array and you've got sparse values, then it's really, really fast. But if you've got a bad hash, it's really going to punish you, and especially if you're removing, then it's going to extra punish you. So yes, you must have a good hash to be able to use this system well. Okay, so I think that's the end of my slides. Let's have a look at the actual code. So let's it's called HashMap P2, just because my original HashMap wasn't a power of 2, and P2 just means power of 2, but this is the one I typically always use now. And it's mapping a key to a value, but you could equally use it for just a set of just keys. So these are just the range iterators for the range base 4, not very interesting. But basically when you're iterating over, where's my little array? When you're iterating over, you literally just start at the beginning and skip empty values. So it's pretty fast, it's really cache friendly. And you can iterate over this very, very fast, even if there's loads of sparse values. It's really good. So that's the range base 4. And the range base 4 just literally stores an index and increments it. So yeah, nothing interesting there, which is good, because we like simple code. Constructor, not very interesting. Let's actually look at the members first. So, like I said, it's an array of pointers. It's actually an array of pointers to pairs. So yeah, the pair is obviously a key value pair, and table is this big table, and it's pointers to pairs. It's an array of pointers. Okay, so and I've just got an allocator for the pairs. So like I said, this is really, really cache friendly, and we never have to actually move a pair. We're just moving the pointers around. So we obviously got capacity and a count, and the shift I'll explain in a minute. And just some diagnostic stuff in debug, so I can check it. So I can check this, checks how many times on average it does an iteration. So if it finds the value straight off and it's there, it's just 0 iterations. But if it has to check the next one, obviously it's 1 iteration, and you can see how many are on average iterations. And ideally it shouldn't ever be more than about 2 on average iterations. So you don't want loads of these. Usually it's just 1 or 2 or none. So that's just to keep track of how well the hash is performing. So in debug, this will log out a message if it goes more than 2 or 3 or something, and print a warning, and then I'll go and check my hash function and try and improve it. So this is the margin. Like I said, it's a quarter. So as soon as it reaches over a quarter full, then it will resize up to the next size, reallocate a new table, copy all the values in, and then we'll be in a nice, good position with sparse values like that. So let's look at the add, which is really simple as can be. Oh, another question. Any reason you're not using unsigned int for count capacity? I typically don't in anything unless I need to. I did go through a phase of using unsigned ints for things like that should be unsigned. And I just kept running into bugs where I would be using -1 or something, or iterating in reverse using decrement and checking it was above 0, things like that. I just don't find it useful, to be honest. It's not worth the hassle. Obviously you can have an array of a slightly bigger size, or twice the size, if you use an unsigned int, but you end up running into bugs where you start using indices as ints. So yeah, I mean, you could use uints, but I just prefer to use ints everywhere unless I really have to. And to be honest, I have got a few container classes which I do need to cope with sort of more than 2 million or whatever it is values, and then I'll just use an int64, to be honest, rather than a uint. I just don't find it's worth the hassle. So I was going to show you the add. That's the remove. So obviously the key has a hash, so we just get the index of where it's going to go. Just checking. Oh yeah, so it's the, just reminding myself of the code. The get item index, that's why I was a bit confused then, because I was thinking that was, say, returning index 5 for that, but it's not. It's actually returning the index of where it's going to go. So this would return the index 6, even though the hash is hashing to 5. So this is where the while loop is. So while the item's in use, and the key doesn't equal the key we're looking for, so because it could already be in the map, and if it is, we just replace it. So this is doing the iteration, like here, it's just iterating, trying to find an empty slot that we can put it in. And obviously it has to cope with the wraparound. And again, the wraparound, because it's a power of 2, is just an AND, so it's masking capacity -1, rather than using a modulo divide. Like I said, this is just the check, to check how many times we're iterating, so you can ignore that. So yeah, that's as complicated as it gets, really. I'll show you this hash code in a second. Let's just go back to the add. So if this is saying if it's already in the table, and we just replace it, so which is not typically the case. So what we need to do is, at this stage, we need to grow. If we've reached our margin of more than a quarter full, then we need to grow the table. And then we need to get the index again, because obviously it's going to be a new index because the table has resized. So then we just allocate a pair from our allocator and stick it in the index. And that's as simple as that. So adding is really, really quick. And the same for getting a value. We just do the same thing. If we're trying to get a value of this key, and we just do the same thing again, getting the index. If it's in this table, if it's in use, then that's our value. And if not, we just return false. So adding and querying are incredibly fast. Before we go to the remove, let's have a look at the hash. I'll explain the KnuthHash. Get hash code. Hopefully you can see that. So the key obviously has a get hash code function, and I do actually use uints for the hash code because there's no danger of ever going negative on them. And you'll notice that this KnuthHash has a shift as well. Now, let's have a quick look at this function. So this hash is just multiplying and then shifting. And something that lots of people get wrong, and I did for a long time, was I thought, oh yeah, just KnuthHash is just multiplying by a prime, just like lots of hashes do, and that's it. And so people just multiply by this number thinking that's a prime. Well, first of all, that's not a prime. It's actually some special magical number, something to do with the golden ratio. And it's a very special number for 32-bit hashing. So I won't claim to understand this or why it works. I don't think many people do know why it works. But it's a very good value for hashing things into a 32-bit number. The other thing people forget, like I said, is the shift. They just think, oh, I just multiply it by a prime and I'm done. You have to shift it down. And the reason for that is whenever you do a multiplicative hash, most of the information gets shifted to the top bits. And so if you just took the lower bits, like I originally told you, if you just take the lower bits of the hash after doing this multiply, you're actually taking the worst bits of it, and you need to take the better bits. So after you've multiplied, you need to take the higher bits, which is why we shift it down. And it's not just a constant shift. The shift depends on the size of the table, and that's really important. So otherwise this magic number just doesn't work well at all. You have to shift it down by the size of the table, how many bits there are on the table. So the bigger the table, the more you shift it down. Now don't ask me why that works, but it does, and I've tested it. It's not a huge difference, but it's definitely worth having. So that's just something to keep in mind. There's a lot of wrong information on the internet about KnuthHash and what number to use. I mean, I saw one place where they said, oh, I changed this because it wasn't a prime number, so it must have been a mistake, so I changed it to a prime or something. No, don't do that. It's not supposed to be a prime. You have to use it as it is with the shift, and then it works well. So anyway, enough of that. So, because sometimes when I'm using this HashMap, I will just pass in an int. So often I use handles for things which are just incrementing ints, and I'll just pass that int as a hash into this table, and then it gets multiplied by this KnuthHash, and a good hash is generated, and that works quite well. So just for sequential ints, but obviously it'll work well for anything, any like a string hash you pass in, you can just do the same thing, and it's not going to make it worse, and it's going to make it better because you're shifting it by the size of the table. So what this hash does is it says, okay, you give it a hash as an input, and the output is saying this is going to be a good hash for the size of table you've got, and that's important for this algorithm. So yes, that's the KnuthHash explained as the best I can. I won't claim to understand exactly why or how it works, but that's what I do. And then obviously you just AND it with the capacity -1, because the table is a power of 2, you can do that, and that's very fast. So as you can see, it's incredibly fast. That's the extent of the algorithm for adding and querying. Right, so let's look at the remove and then we're done, I think. So again, we get the index in exactly the same way. If it's not in use, then this table, the HashMap doesn't have the key, and we just return false. So we get the pair. So like I said, we first need to scan back, as I said in this slide here. Wherever we start, if we're removing number 5, we have to scan back to the first one in this array. So we scan back until we find an empty pair, and then it's the one after that. So that's what that's doing. They're scanning back until we find the one we want. So then we find the index. Then we're going to iterate through this array until we find, sorry, we're going to start at number 5 and we're removing and iterate through until we find one that we can replace into the whole. So let's go back and see a better example. So say we're trying to fill a hole in number 6 because we've removed it. We scan forwards until we find one. 7 can't go there because 7's already in its proper place. So we go to number 8 and we find that green one there, and we can put it in there, and that's what that code is doing. So it's literally just it's checking the value is in range. So the range is from the start to the end. The range is from the start to the one we're removing. So we can only move this one because it's in the range between 3 and 6. So that goes into there. So that's what that range check is for. And obviously, like I said, that's got to cope with wraparound at the beginning and the end. So then we find our swap index, and so we found it. That's good. And then we swap the item. So again, like I said, this is just swapping a pointer. So it's not expensive at all. And if we didn't find one to move, then we're done because there are no holes, and that's fine. If we didn't find, if these 3 weren't here, then we would just get to 7, and then 8 would be empty, and we'd be done. We wouldn't need to actually move anything. So we only need to move until we only need to search until we find an empty hole. So if we found an empty one, we just break and we're done. And then obviously we need to keep doing it, and that's what this for loop is for here. So we're going to keep going around this loop, like I said, removing and filling any holes multiple times. But hopefully we'd never need to go around this loop more than once or twice. So that's about it. And then obviously we need to free. It's only doing one free because we're just freeing the one we're actually removing. So in this case, number 6, we're just freeing that pair from the allocator, and that just goes back on the allocator. So we're not actually doing a free in global memory. We're just sticking it back on the allocator so it can get reused. Because that, as I said, that's just a fixed size allocator for pairs. And I think that's it. We're done. So yeah, talked about the wraparound. Don't think there's anything else to talk about. Oh yeah, we didn't talk about the growing, but that's pretty straightforward, as you can imagine. We just allocate a new table of the new capacity and then iterate through our old map and just add them to the new map and then free the old map. So very simple. And again, we're not copying items around. This is all just dealing with pointers. So the time will just be spent in this get index. So getting the new index after we've resized the table to be bigger, we just need to find the new index. So that'll be what takes the time in creating this new table. So Just some extra helper functions like operator equals, assignment operator. Not used very often, but occasionally it's useful. Reserving, obviously, like I said, really important to reserve these tables so you don't resize any more than you really need to. And then these are just the accessors to get values for a key. So you just get the item index and there it is. There's the value. So really, really simple. That's the remove, contains, try get value. Try get value is a really nice pattern to use. And I use it pretty much in all my map classes and containers and stuff. So it just means you can return a bool if you've got it, and if you have, it fills in this value. It's something I sort of copied from the C# way of doing things in their container libraries, and I really like it. It's a really nice pattern to use. So you don't have to first do a contains and then do a get. This is a contains and get in the same operation, pretty much. If it's there, it will get it. If it's not, it will return false. So it just saves on doing that extra lookup in a table that you often have to do otherwise. Clear, and yeah, that's it. So someone's asking about the KnuthHash, about wrong information on the internet. Do you have any pointers to good resources? No, sorry, I can't really think. I didn't save the resources I had. I can try and look something up and put something in the comments if you want, because there are a few really good. I'm just trying to remember what it was. Yeah, there were lots of wrong ones, but one or two really good ones that explained it in greater detail than I've gone into here. So yeah, I'll try and find that and stick it in the comments, because it's definitely worth a read. Because it's a fascinating thing of how it does actually work and why that number was chosen to be so good, and why the shift is so important, the thing that most people forget to do. So yeah, I'll try and find that for you. So, okay, I think that's it for today, unless anyone's got any more questions. And I think next time I'll do my red-black tree implementation, which is I only pretty much use two mapping classes. I use the HashMap, which I just showed you, and I use the red-black tree for the standard kind of STD map type thing. And they both have different benefits. I use the HashMap most of the time, but occasionally I'll use the red-black tree. Sorry, so I'll probably go through that next time in a similar way. We can see how it works. But I really like writing container classes. It's something I find fun. I think it should be a sort of rite of passage of every programmer to have to at least write one container class. And you know, it really doesn't take as long as you might think. Okay, someone's just put something in the comments about multiplicative hashing, which is good. I haven't heard of that book actually. Yeah, I mean, that's another thing. We could do a whole stream on how to create good hashes. It's something I've looked into quite a bit for the 10x code base, because, you know, as I said, I'm using these hash maps everywhere in the code base, and so much of the speed of the 10x parser relies on good hashing and good hash generation. So that's definitely something we could do a stream on if people are interested. So yeah, if that's it, no one's got any more questions. Like I said, follow me on Twitter. I'm probably going to do a 10x live stream on Saturday if you're interested in following 10x development. And if you are, please subscribe and join our 10x Discord. So, okay, until then, take care, and I'll see you next week.